We'll be hearing from 3 presenters in the area of speech technology, 2 in the area of data development, and 2 in the field of speech science, showcasing cutting-edge work that I'm confident will inspire fruitful discussion. I kindly ask all presenters to adhere to the allocated time to ensure a smooth and engaging session. Each presenter will have 13 minutes for their presentation, followed by a 3-minute question and answer session. To keep us on track, presenter will be reminded when they have reached 10 minutes, and then we respectfully stopped at 13 minutes. After each presentation, there will be a question and answer discussion, so please prepare your inquiries accordingly. Without further ado, let us begin to our first presentation. It's my pleasure to introduce our first speaker, Wang Xixi Zhu, who will be sharing research in the area of speech technology with title Toward Natural Emotional Text-to-Speech System with Fine-Grained Non-Verbal Expression Control. Please join me in welcoming Wang Xixi Zhu. Thank you.
I'm Wang Xixi from NACE. Today my presentation topic is Toward Natural Emotional Text-to-Speech System with a Fine-Grained Nonverbal Expression Control. Here is today's outline. We will start from background first. So for the existing emotional TTS now, they already have made significant strides in generating emotional speech. Like for the text, nice to meet you, we can control the prosody feature for that, for control the pitch, the speed, and energy. However, most of these emotional TTS now, they focus on the verbal content control. They ignore important part for also convey the emotion, the nonverbal vocalizations. So what is nonverbal vocalizations? It's referred to the vocalizations contain no linguistic informations, like laugh, cry, and scream. They provide a spontaneous, authentic emotional expression and will be used in our normal communication. So for also build the human-like emotion TTS, the non-verbal vocalization is necessary. In response to the need, there is already have some NV dataset exist. So for example, for AMI dataset, this is an English dataset. They provide 100 hours of meeting records, but narrow scope of the NV dataset. Mostly is laughter and coughs. And for the JNV dataset, this is a Japanese NV corpus. But they have some culturally specific expression, like for their angry NV, they use onore, it's a Japanese word, make it unsuitable for English TTS. And NV TTS dataset, this is an English dataset, but they suffer from have some background noise for part of data. And because of the this old dataset, they only use coarse-grained text. So because of this dataset limitation for the emotional TTS with NV, they only can use a coarse-grained text, only choose the type of the nonverbal vocalization, like just a laugh or just a cry. However, in some situation, we want to control it more precisely, control the nonverbal vocalization, control how long is the laugh wheel and how many times we will laugh. So for address this limitation, in our work, we construct a fine-grained NV data and build the fine-grained NV emotional TTS. Here's more detail. So for constructing the fine-grained non-verbal expression data, we reprocess from existing corpus, EAR's corpus. They have a subset comprised exclusively of non-verbal audio without transcription. And for this time, we focus on the female speaker. So for their non-verbal audio original, they have like 360 audio. Each is contain 10 to 12 seconds. It's kind of long, so we do segment for this and to get 39 audio, each around 2 to 6 seconds. And for creating the non-verbal transcription, first we use Whisper ASR model to get the initial transcription. And then we do manual verification for that to get the final transcription. And as a result, we have the 6 category of the non-verbal vocalizations. And for their transcript, so for chowing, we have uhu, yo. For yowling, we have hey. For laughter open, we have ha. For laughter closed, we have ha. And for crying, we have weep, sneeze. For screaming, we have ah. And so for fine-grained tag, so compared with the coarse-grained tag, they only have a simple style level tag, or have like a style level tag, vocalization type and control, frequency and duration control. So for like in the fine-grained type, we can choose what kind of transcript we want to use with the same like style. And for the control, the discrete sound, like for the frequency control, we can specific token repetition, like for ha, we can choose how many ha we use in our tag to determine the count of the sound. And for the continuous sound, like u, we can repeating the final character for u, we repeat the u to precisely control the sound's length. And we build the like non-verbal emotion TTS. So for normally, the most of the emotion TTS, they only use the verbal, use verbal content, as the input. And for some emotional TTS, they can use the cross NV. They have a simple like NV style with the content, with the verbal content as the input. And for proposed one, we have our fine-grained NV tag with the content, verbal content as the input. And for model understand the fine-grained NV tag, we design an NV processor to process it to the NV token. And for the NV processor, we have 3. First, style parser to recognize the NV style, and then discrete unit parser to count the occurs of the discrete vocalization, and the duration parser to calculate the duration based on the continuous vocalization. And after NV processor, we will get a NV token and use it to our like emotion TTS. And here is our experiment setting. So for let our model can also use synthesize the verbal content speech. We also train it on the verbal dataset, a mixed English female only data with the expressor dataset, Semon dataset, and ESD dataset. And for compare with the before cross-grained NV dataset, we use the NV TTS dataset. And for our fine-grained NV dataset, we use our proposed data. And for TTS backbone, we use GRAD TTS as a backbone with the emo embedding, make it can synthesize the emotional speech. And for evaluation metrics, we use subject evaluation with 15 participants. And for the speech naturalness, we use naturalness mean openness score, NMOS. And for the expressive, for the speech, we use the emotional mean openness score, EMOS. And for the accuracy, we use the emotion accuracy. So for the accuracy, we test like, we give the listener the like synthesize the speech, but without tell them the like emotion level of that synthesized speech. We ask a listener to do like recognize what emotion is this speech is, and get the emotion label from the listener and compare with the real emotion label to calculate the emotion accuracy. And here is our result. So let's listen some sample first. Please play the only verbal sample.
You're so funny. You're so fun. You're so fun. You're so funny. You're so funny.
Yeah, and please play the sample of verbal cross-grain envy.
You are so funny.
And please play the verbal with the fine-grained envy sample.
You are so funny.
Yeah, that's a sample. And for the result, for the nature's MOS, you can see even for our proposed one, it's a little decrease in the natures, but for the expressions and the accuracy, it have good improvement. Especially for the accuracy, it's achieved 82%. And for the more specific analysis, so for like emotion, we evaluate in 4 emotions. For cross-grain envy, it only have 2 emotion results. It's because for envy TTS dataset, they only have a laugh and crying is emotion-related non-verbal vocalizations. And for our proposal fine-grained envy, the EMRs, you can see for the result, except the anchor, the happy, sad, fear is all achieved around 4.2 scores. And for the accuracy, you can see also compare with the only verbal and the cross-grain envy or fine-grained envy, the accuracy is very good. And for the especially for the set, it's achieved the 98% accuracy is almost perfect. And for the fear emotion is have around 30% improvement. And for the reason why angry, the performance it doesn't improve much. We think it's because, so for the happy, fear, sad emotion, they all have emotion-related non-verbal vocalization. Like for happy, we have laughing and cheering, and for fear, we have a scream, and for sad, we have a crying. But for angry, in our experience, we use the yelling as the angry-related envy, but sometimes yelling will not make people directly think it's angry, so some people misrecognize it to the happy. And we also do preference evaluation for it. We do different combination with our envy to ask listener to rank them based on their performance. And here is a happy emotions result. You can see for the happy emotions envy combination, the cheering is all preferred over the laugh. And for the sad emotion, you can see the first one is like a complex, multi-part expression was more highly preferred. And here is our conclusion. So in our work, our contribution is construct fine-grained non-verbal vocalization expression data and established an emotional TTS enable model to precisely use the fine-grained envy. And for the result, the synthesized speech from our fine-grained envy exhibit the better emotional expressions and the recognition accuracy compared to both verbal only and the traditional before the cross-grain envy one. And for the envy preference test, it's revealed that actually listeners have some distinct preference for specific envy expressions, demonstrate that actually fine-grained control is necessary to match user expectation for authentic envy performance. Yeah, that's all. Thank you very much. Any questions?
Okay, that was an interesting presentation, Ms. Zhu.
Yeah.
Okay, big applause to Ms. Zhu.
Thank you.
Okay, now I'd like to open the floor for the questions. Is there any question from audience? Oh, not yet? So let me ask the first question then. Okay, your paper highlights the emotional recognition with fine-grained non-verbal cues, right? And the accuracy is tend to higher than before, but there is a trade-off. in the naturalness decrease, right? A bit decrease in the naturalness, EMOS, not EMOS, NMOS.
NMOS,
right? Yes.
yeah.
Okay. Now, what do you think? Which aspect of the fine-grained nonverbal cues that make this decrease in naturalness?
Actually, it's because for like our fine-grained NV data, you can see actually it's only have a 700 utterance, right? So it's kind of small. So this like a small data set, so it makes non-verbal is not so unstable. So and for like so people when they listen that not unstable non-verbal, so they feel it's a little decrease for the natures. So that's why I think the score is a little decrease.
Oh, okay. So in the future, what are you planning to maybe make it balanced to make the accuracy higher, but also the naturalness is not decreased?
Yeah, we will try to try to design some like a special module, make it more better training for the non-verbal vocalization, make it stable, so the natures will not decrease.
Okay.
Yeah.
Thank you.
Thank you.
Okay. Maybe I would like to ask the audience again. Any questions? Nope. So there is still time? Yes. Okay, maybe I can ask you another question then.
Okay, thank you.
Okay. So you utilize ears corpus, right? So this corpus is primarily recording in controlled situation. In controlled situation and recording in controlled situation. So how might you finding to generalize to more spontaneous speech? It's not in the recording situation like that?
I think it's recording situation.
Yeah, so how about the spontaneous, for example, in the real life conversation? So
Yeah, but there is like for spontaneous one, we want to use some, but always there's no data set for these kind of
Okay.
things. Yeah.
okay, that's all. Okay, any other question? Time's already up. Okay, thank you,
Yeah.
Mr. Zhu, for your presentation.
Thank you.
Now we move to the next presenter. So please welcome Saddam Anais Shakil, who will presenting his research on stage-wise acoustic linguistic fine-tuning for overlapped speech recognition, thus ordering matter. Please welcome Mr. Shakil. Time is yours. The slide, please.
Okay. Good morning, everyone. My name is Saddam Anais Shakil, and I'm from Bandung Institute of Technology. Today, I'm excited to present our research titled Stage-Wise Acoustic Linguistic Fine-Tuning for Overlap Speech Recognition. And this work was a close collaboration with my supervisor, Dr. Desi Puji Lestari, as well as Professor Sakriani Sakti. The core question we'll be answering today is simple but a critical one. When you have a complex audio language model, does the order you fine-tune the components in actually matters? So let's start with the problem. In a clean single-speaker scenario, ASR is almost a solved problem. And a modern system can achieve a word error rate of as low as 5.5%. But the moment you enter a real-world scenario, and one additional speaker, the performance completely collapses. The error rate explodes from 5.5% to a nearly 85%. This clearly shows that recognizing overlap speech is still a major unsolved challenge. The traditional approach has limitations. Pipeline methods, where you try to separate speakers and then transcribe it, suffers from error accumulation. If the separation is bad, the transcription is guaranteed to be bad as well. A more recent end-to-end model are better, but they often act as a listener that lacks deep linguistic understanding. They struggle to resolve ambiguity when the original audio is truly distorted. This limitation brings us to the most recent approach, bimodal audio language model. The idea is to combine between an audio encoder, which acts as the ear of the system to perceive the audio wave, and we connect it to a large language model, which acts as the brain to provide deep linguistic understanding. The brain can in theory resolve this ambiguity that the ear alone cannot handle. But this new architecture creates a new problem. How do you best train it? Could you train all the components together at the same time? Or you could train it in stages. This stage approach, where you fine-tune components sequentially, is very common, but it raises a critical, unstudied questions. What is the optimal way to fine-tune these components? Does the order actually matter? Should you fine-tune the ear first to get a good audio signal and then train the brain, or you should fine-tune the brain first to understand the task and then train the ear? This is the central gap of our research aims to fill. So to address this gap, our research is focused on 3 specific questions. First, and most importantly, does the order matter? Is it better to fine-tune the acoustic model first, which we call it the acoustic linguistic approach, or is it better to find the language model first, which we call it the linguistic acoustic approach? Second, how do these sequential stage strategies compare to a joint approach? And finally, what is the trade-off? We'll look at the relationship between the final accuracy as well as the final computation cost. Okay. To answer these questions, we designed an experiment around 2 main sequential strategies, which you can see in the diagram. At the top, we have the acoustic linguistic strategy. In stage 1, we fine-tune only the audio encoder, and then in stage 2, we freeze the audio model and fine-tune the LLM, testing both the full LLM as well as the LoRa version. And at the bottom is the reverse. The linguistic acoustic strategy here in stage 1, we fine-tune the LLM first, testing both the full as well as the LoRa variant, and then in stage 2, we freeze the LLM and fine-tune the audio encoder. And we will also compare the result of this research to each other as well as to a joint training approach. And let's look at the setup. First, we didn't build a model from scratch. We use an existing model, Qwen2 Audio. It is composed of a Whisper large version 2 encoder, a linear projector, as well as a Qwen2 7 billion language model as the decoder. For our dataset, we use LibreMix, which is a well-known dataset for this kind of task. It is created by taking an audio from the LibreSpeech dataset, mixing it together, and then adding a background noise. The model task is to transcribe both speakers in a single pass. The output format is using serialized output training, where speakers want transcriptions followed by special speaker change token, and then speakers to transcription. So before we start fine-tuning, we establish a baseline. Now, a direct zero-shot task was invisible since the pre-trained model isn't designed to produce a special speaker change token or the serialized output format. So we gave it a few examples to see how it would perform, and the result was a word error rate of 54.96 AQR. So we began our experiment with stage 1 of the sequential fine-tuning. Here we are only fine-tuning one component at a time to see what its initial impact is. And the results are very interesting. If we train the acoustic model only, we get our strongest initial results at 11.0% wear. This intuitively makes sense because the model must first learn to hear the overlapping signal. If we train the linguistic only model with full fine-tuning, it starts a bit weaker at 12.74%. But look at the linguistic LoRa strategy. In isolation, it performed worse, almost 22% in wear. And this is driven by the substitution, it's the insertion around 8%. This shows the LLM struggles with poor quality audio features and essentially hallucinates or adds extra words. So after stage 1, the evidence points to the acoustic strategy being the best starting point. But does this initial advantage hold after we complete stage 2? Let's find out. The answer is no. In fact, the trend completely reversed. Looking at the linguistic acoustic full fine-tuning strategy, this is the approach that started weaker in stage 1, but after stage 2, it is now our best performing model, achieving a word error rate of 8.96%. The result is also consistent. The linguistic acoustic approach wins the full fine-tuning settings, and it also wins on the LoRa fine-tuning settings. And this brings us to the next takeaway. The LoRa is highly efficient. The linguistic acoustic LoRa model achieved 9.07% wear, which is nearly identical to the best model. And this proves two things. First, the order is critical, and the second, the linguistic acoustic approach is the superior strategy. And why does this linguistic acoustic strategy wins? It started weaker but ended up on top. Our hypothesis is that in stage 1, we teach the model what to expect. By fine-tuning the LLM first, we are teaching it the specific vocabulary, the syntax, and the conversational patterns of the serialized task. The language model learns the structure of the correct answer before it ever processes the difficult audio. Then in stage 2, the fine-tuned audio model is guided by the knowledgeable LLM, which already knows what a coherent output should look like. This leads to the results where the audio model learns to extract and prioritize the specific acoustic feature from mixed signals that are most relevant to the linguistic structure. So if our linguistic acoustic model is effective, what errors still making? So to better our understanding of the best performance model, we did a deep dive into its error distribution. Looking at the breakdown, over 91% of all errors are substitution. That's the model recognizing the wrong word. And another important insight is the deletion and insertion is less than 4.5% each. This means our model is good at the structural task. And the primary challenge is the model's tendency to resolve ambiguity into alternatives that are not acoustically similar but also contextually viable. For example, a model might transcribe the phrase "a withering flower" as "a withered flower," where both grammatically correct sentences which validity depends on a broader, unstated context. Finally, we need to talk about the cost. Is that 0.11% improvement model worth it? And our best model achieved 8.96% wear, but it's also the most expensive, costing 1,200 GPU hours. And the linguistic acoustic LoRa, it's only 0.11% worse, but it saves over 340 GPU hours, 28% reduction. And this is a great trade-off. And if you need efficiency for rapid prototyping, the joint training is the cheapest at 532 hours. But you take a performance hits. And as you can see, the acoustic linguistic are simply inefficient. They cost the same as our best model, but perform the worst. And this entire trade-off is much easier to see it visually. Now, we can see the entire trade-off. On the Y, we have where, and so the lower is better, and on the X is computational cost, so the left is better. And we can immediately see two key findings. The acoustic linguistic, which are on the gray and red, are inefficient, clearly inefficient. And second, our three other models from what we call efficient frontier are the only strategies worth considering. And this is what the trade-off looks like. To move to our balanced linguistic acoustic LoRa model, we have to pay an extra 334 GPU hours. In which return, we get a reduction of 3% relative, 0.28% absolute reduction. But from the next step, from linguistic acoustic LoRa to linguistic acoustic full fine-tuning, it costs 343 GPU hours, but it only gained 1.21% relatives. And this is a classic case of diminishing return where we pay more for less. So to conclude our findings, we have two main takeaways. First, our primary contribution is the evidence that the fine-tuning sequence is not just a minor detail, it is a critical factor. in model performance, and we demonstrate that linguistic acoustic strategy consistently outperforms other approaches. Second, our analysis provides a framework that you can use to select strategy based on your goals. If you need an absolute maximum accuracy, the linguistic acoustic full fine-tuning strategy is the choice, though it comes at highest computational cost. However, for most real-world applications, we recommend optimal balance, where the linguistic acoustic LoRa is the sweet spot, nearly identical accuracy with significant 28.3% reduction cost. And finally, if you are in a resource-constrained environment, a joint training strategy is your ideal approach. Finally, our works open up several differences for future works. We should test this finding on more complex real-world scenario where 3 or more speakers. And secondly, we need to test it on its generalizability by evaluating this framework on non-English datasets. This concludes my presentations. Thank you.
Okay, thank you, Mr. Shakila, for your sharing your work with us. Okay, now I will ask the audience. Is there any question? Okay, please.
Okay, thank you. So I have 2 questions. So the first one is, I want to know whether you think this approach would be extensible to other adaptation to ASR, for example, like language extension or domain adaptation. And the second question would be, I wonder if you have considered not fine-tuning the whole encoder layer, but maybe like freezing the layer up to like several layers and then just fine-tune the few most bottom layers. I just wonder whether you have considered that or just decided to do like a full encoder fine-tuning. Yeah.
Okay, let's start with the second questions. Yes, I have actually considered it. We actually considered to use LoRa first on the audio encoder as well, but we didn't do it eventually because again, on the audio encoder size for training isn't as big as the LLM, so it's still feasible to learn it, train it fully. Yeah, and I'm sorry for the first questions. Can you repeat it again?
I wonder whether the technique like doing like linguistic fine-tuning and then acoustic fine-tuning would be transferable to other ASR adaptations, maybe like language extensions or domain adaptations.
One of our future works as well. We want to test it whether it will be transferable as well to other domains, maybe not just for the LLM, for the bimodal LLM and audio, but probably other bimodal as well. Yeah.
Audience, is there any questions? Okay, please.
Thank you very much for your talk. So I have one simple question. So what language did you use for evaluation? So what language did you use for the evaluation? Which language?
Oh, what language?
The language you use is English from the library speech datasets. Yeah.
Okay, so that means you use the several languages?
No, we only use English for this.
Indonesian language?
English.
English, oh, sorry. So because I'm also interested in applying your method for the low resource language, so I'm interested in your methodology. So I'm wondering whether we can apply your method for such a language. So that's why I asked which language did you use in the evaluation. Okay. Anyways, thank you very much.
Thank you very much as well.
Yeah, it's interesting. Yeah. So you are using English. How about other languages? What do you think about for example, for Indonesian, we don't have any good LLM, or what? Why you use English, not Bahasa Indonesia?
First of all, because the task is about overlap speech recognition, and the LibriMix dataset is already a big dataset where people almost use it for this kind of task. Yeah.
Okay, thank you. I think time is up. Thank you, Mr. Shakila. And big applause. Okay, next we will have a presenter still in the area of speech technology. Please welcome Hin Min Wang to share the research in exploring the impact of data quantity on ASR in extremely low resource languages. Please, time is yours, Mr. Wang.
Okay, thank you, Chairperson. Good morning, everyone. I'm Xin Wang from Academic Sinica, Taiwan. I will present a paper entitled Exploring the Impact of Data Quantity on ASR in Extremely Low Resource Languages. So I will present the paper on behalf of my former students and research assistants. Unfortunately, all of them cannot come. Okay, so we know that currently ASR systems are achieving remarkable results on resource-rich languages such as English and Mandarin. However, it is still a very challenging task for low-resource languages, as there's limited speech data for pre-training, SSL model or feature extractor, or paired speech text data for fine-tuning or training the downstream models. So the research question here is that can we find some research utterance in other languages that sound similar to the target language as pre-training data for the speech encoder. So in this work, we evaluate our proposed method on two low-resource languages spoken in Taiwan, CDIC and AMIS. And we follow the multilingual super benchmark to curate multi-speaker ASR datasets. So following the setup, we have for each language, we have a 1 hour training or a 10-minute training set. And these are used to evaluate the amount of training data needed. And there's also a validation set and test set. Both have like 10 minutes of speech utterance. And for your inference, Super is leaderboard to benchmark the performance of self-supervised learning models on various speech processing tasks. It covers a wide range of speech processing tasks for only English. And then it utilizes frozen SSL features and employ a simple framework for speech processing tasks by learning a shallow downstream model. So the result shows that SSL models can significantly improve performance compared to traditional field band features. And later on, multilingual super covered 143 languages and focused only on the automated speech recognition and the language identification tasks. And this slide, the first table shows the data set used in the ML super benchmark. There are 143 different languages. And for each language, this is 10 minutes training and 1 hour training, and the development set and test set both have 10 minutes. And the second table shows all the SSL models that can be used for feature extraction. And the right-hand side is a GitHub called S3PRL, and you can use the toolkit covered by all the model covered by the toolkit, including the left-hand side, all the SSL model, and right-hand side, all the model architectures for many different downstream tasks. And in this work, we propose to select the best K-hours speech utterance from the ML super multilingual data set to fine-tune the SSL model before we apply it to ASR. So here we say fine-tune ASR model, or we can also call it continue pre-training the ASR models. So in the first step, we extract language embeddings from speech utterance of the ML super data set and also the training data of the target language. And in the second step, we build a one-class classifier using only the language embeddings of the target language. And the third step, we rank the utterance of the ML super data set by applying their language embeddings to the one-class classifier. So we only select the best subset to fine-tune the SSL model. And we evaluate 3 different type of one-class classifier. The first one is one-class support vector machine, which aims to construct a hyperplane in a high-dimensional feature space that includes the majority of data points while maximize the distance between this hyperplane and the origin. So the data point falling inside the hyperplane is the boundary are considered as anomalies. And for the second one-class classifier, which is isolation forest, it leverages an ensemble of isolation trees to detect anomalies. Okay, and the third method is called deep support vector data description, which utilizes a deep learning neural network to learn a hypersphere in the feature space that encapsulates the training data while minimizing the volume of this hypersphere. Okay. In addition to the 3 classifiers, we also propose an algorithm to fuse all the decision of the 3 classifiers. That is, it will prioritize utterance that rank highly in all the classifiers simultaneously. Okay, so for experimental setup, we use the top K hours of speech data selected from the ML super multilingual data set to do this continued pre-training of the SSL model. And then the refined SSL model was used to generate SSL features, enabling training of the downstream ASR model using target language, speech, and the transcriptions. And we use FAIRST toolkit for pre-training, and then they use S3PRL and ESPNet for the downstream ASR task. And for language embedding extraction, we use TitanNet LED, which is also called EmberNet, developed by NVIDIA. And for ASR model, the downstream ASR model tasks follow the ML super design. So we use the frozen SSL representation. And this representation will be weighted and summed using the learnable weights. And the ASR model consists of a simple model, just consists of CNN layer to downsample SSL feature sequence to half its original length, and 2 transformer layers and 1 feedforward layers. And the ASR model was trained with CTC loss and ADAM using ADAM optimizer. A speech augment was applied to the SSL features. And this slide shows the benchmark slide, benchmark results for AMIS and the CDIC. You can see from the table, the first column is the different types of SSL model, and the second is the size of the model, and the third column denotes the number of training language. So some of them are monolingual models, and some of them are multilingual models. And the fourth column shows the result for AMIS 1 hour training, AMIS 10-minute training, AMIS 1 hour training, and the CD 10-minute training, and the CD 1 hour training. And the result with this orange background denote the best performance for each specific language and the training condition. And the result with green background shows excellent performance. Okay, so from the table, we can see that generally Huber model outperform wet-to-wet models. So when trained on the same data. And the second observation is that larger SSL model provide a moderate but stable performance improvement, especially in the 1 hour training setting. and multilingual pre-training has a positive impact on ASR performance in low-resource settings. However, we also found that large SSR model, while generally outperform their smaller counterparts, they also exhibit a tendency to overfit when trained on limited data. So we can see that the fitting was particularly evident for models like Chinese Web2Vet large, Vet large 23, and XLSS3, SR300M, and the Huber large. So from the table, we can see that, for example, and then we propose to mitigate this problem by shrinking the downstream ASR model by having the number of attention heads and reducing the feed-forward dimension. So by doing this, we can see that when we use Chinese Web2Vet 2 large, the character error rate can be reduced from like 89 to like something like 15%. Okay, so and this slide shows the main result for the proposed method, and the figure looks complicated. We can see that the left-hand side shows the results for the AMIS, and the right-hand side shows the result for CDIC. The blue figure shows the results of the, it's difficult for me to see. Okay, the blue color is the result for 10 minutes training, and the red color shows the result of 1 hour training. And we can see that for each, here we compare 3 data selection methods. The first figure is a random selection, the second is a deep SVDD, and the last one is the algorithm one. So we only choose deep SVDD here is because it is the best among the 3, and when we didn't show the performance of other models due to the page limit here. And for each figure, the x-axis is the size of used for the data size used for fine-tuning the SSL model, and the vertical axis is the character error rate. So from the figure, we can see that basically increasing the amount of pre-training data generally leads to improved ASR performance. And expanding pre-training data to 64 hours significantly reduced character error for both languages, highlighting the advantage of more data across different languages. And our approach, including like a deep SVDD and the algorithm 1, outperform random selection in almost all experiments. And although we find that algorithm 1, which is a fusion of a 3 classifier, is not always superior to the best classifier, deep SVDD, but we did observe an obvious gap in 16 hours pre-training for AMIS, which is to show the up figure of the left-hand side. Okay. Okay. So in conclusion, so in this paper we constructed ML super style speech corpora for 2 low-resource Australasian languages, AMIS and CDIC. We also propose a data augmentation strategy to improve low-resource ASR. So this strategy utilizes one classification method to select acoustically similar speech utterance from a multilingual corpus for continued pre-training of the SSL models. And our results show that while the current performance improvement is not significant, the positive correlation between the amount of pre-training data and the ASR accuracy actually highlight the potential of this approach. So this is all for today's presentation. Thank you.
Thank you, Mr. Wang, for your valuable presentation. So the implication of your finding are quite significant for ASR for extremely low resource languages, right? Okay. Is there any question from the audience? No? Okay, maybe I will ask you the
Okay.
question again. Okay, so Mr. Wang, your classifier, you use classifier to augment your data, right?
Yeah.
Using similarity, phonetic and phonological. So do you have any thought or other methods, not only using that kind of classifier? So what happens if we use, or maybe if we have a low resource language but doesn't have many other resource languages that's similar, phonetic and phonological?
Okay.
So what?
Okay, so currently in our experiment, we only use ML Super because we want to add our data set into the ML Super benchmark.
Oh,
So
okay.
we follow all their setup. And actually, if we want to apply this approach to do data augmentation for a specific language, it's not constrained or limited to just use the ML Super and multilingual dataset, because the ML Super multilingual dataset only consists like a less than maybe on less than 100 hours of data. So actually, we can use more data. We can use like a data set from Common Voice. There are many different. It's a huge data set for many different languages. So maybe we can apply our approach to select more data from that big database. Yeah, but in our current work, we just want to evaluate whether this approach is effective or not. So we totally follow the benchmark setup of the ML Super task.
Thank you.
Okay.
Yes, please. There is a question from.
Which is like, has about population of 10,000 speakers, let's say. I think one of the
CDIC.
Yeah, CDIC
Yes.
has about 10,000 speakers. So when you're doing an ASR for this, what will be the use cases where ASRs can be used for such languages?
Okay. Actually, in Taiwan, we have like 16 is Formosan. We also call Formosan language.
Right.
And for every language, we want to develop an ASR system and a TTS system for each language. In order to, we also want to somehow preserve these languages. Yeah.
Okay.
Yeah. CDIC is the language that has the least speakers. So this is also why we choose CDIC and MIS. So this is MIS can be considered as the language spoken with the most more speakers, and CDIC is the least one. Okay.
Okay. Thank you.
Thank you.
Thank you for your presentation.
Okay. Thank you.
Mr.
Thank you.
So moving from the area of speech technology, our next presentation will continue our focus on the data development field. It's my pleasure to introduce Yuichi Nishida, who will be presenting the work Lafayette Corpus 1M, a large-scale Tetun corpus to build a low-resource LLM for speech and text processing. Please, time is yours.
Okay. Good morning, everyone. My name is Yuichi Nishida from Gifu University, Japan. So today I will present our work, Lafayette Corpus 1M Plus, a large-scale Tetun corpus, to build a low-resource LLM for speech and text processing. So this is my presentation outline. So I will start from introduction, including Tetun and language, and Timor-Leste. So where they speak the language next, I will talk about research overview. I will introduce a new dataset. Lafayette Corpus 1 Plus, there I will talk about LLM named Lafayette Grammar 3 8 billion. I will show you evaluation results and Finally, discussion and future works and conclusion will appear. So in recent years, large language model like ChatGPT, Claude, Llama 3, and Qwen have achieved remarkable performance across various tasks, like speech processing and NLP processing. But most of these models are primarily trained on English data, and these models often perform worse on low-resource languages. So in this research, we focus on Tetun, official language of Timor-Leste, so which still lacks sufficient support in modern LLMs. So recently, many Asian countries have tried to strike their local languages using continual pre-training, and that is a method that adapts their existing English LLMs to target low-resource languages. So example, Sea Lion, that is the first language model for ASEAN, was developed by Singapore researcher team. However, many low-resource languages are still left behind because they do not have enough text data or computational resources to build the LLM from scratch. So in this work, we adapt continual pre-training approach. So our goal is to create the first large-scale Tetun corpus and use it for continual pre-training to build our Tetun LLM. So let me briefly introduce Tetun and Timor-Leste. So do you know Tetun and Timor-Leste? Timor-Leste is a Southeastern Asian country located in Indonesia and Australia, so which becomes the 11th ASEAN member last month. So there are also more than 30 local languages spoken across the country. So in this work, we focus on Tetun Dili dialect. That is spoken in the capital city Dili and most widely used from Tetun in education and government media document. So Tetun is the second official language of Timor-Leste alongside Portuguese. So this is under the sentence example English to Tetun. So it is written in Latin alphabet, and some words are borrowed from Portuguese and Indonesian, and like an example, friends and amigo. So interestingly, Tetun has no tense and verbs do not conjugate, like talked and qualia, so making it relatively simple in structure. Our research work consists of two main parts. First is building a large-scale Tetun text corpus named Raphael Corpus 1+. Second, developing a Tetun LLM by applying continual pre-training to Llama 3 8 billion using our corpus. So we collect data from various resources, and three categories we collect. First is web resources, Wikipedia and Matplotlib and Rabodyne. So these resources is the main part in this corpus. Second is publications. We include 2 books. Peace Corpus is Small and Discourse Structures of Tetun Dili, published by Tetun DIT. Third is additional resources. Tetun New Testament translation data, Tetun to English. And new transcriptions manually prepared by native speakers. So publications and resources are small compared to web resources, but both of them are very high quality and have English parallel sentences. So we expect language transfer between English to Tetun and may contribute to the improvement. So in total, we collect over 1.1 million sentences. So we performed several cleaning steps to improve quality. So because some web resources were noisy, so we conduct 4 steps. First is NFC normalization. Second is removing URL phone number and URLs. And third is removing a very short sentence by using Llama 3 tokenizer. And last is duplicate removal and min hash functions. So in this step, we follow the same data cleaning procedures used in existing LLM corpora, such as the file, the stack, and the defined web. And next, we conduct continuous pre-training of Llama 3 8 billion using our corpus. The resulting model is called Raphael Llama 3 8 billion. To prevent the model from forgetting English knowledge, so we also added about 120,000 English sentences from refined web. So we used PyTorch and transformers and Anthros libraries and applied LoRa and flash attention 2 for efficient training. Training took 2.5 days on NVIDIA A6000 GPU. So to evaluate our model, we conduct a Tetun to English translation task. So we prepared 40 Tetun sentences with corresponding English references. So we use 3-shot prompting and compared our results with Google Translate, GPT-4 Mini, and the original Llama 3 8 billion. So we use 2 evaluation metrics. First is BLUE. BLUE is translation accuracy between word and word. Second is the BAT score. BAT score is semantic similarity between sentence and sentence. So we also measured perplexity to evaluate language modeling performance. So here are the results. So BLUE score of our model increased from 0.3 to 9.5 after continuous retraining. BAT score improved from 0.85 to 0.93, approaching Google Translate and GPT-4 Mini. The perplexity decreased dramatically from about 500 to 100. So these results demonstrate that our corpus and continuous pre-training significantly improve the model understanding of Tetun. So although our BLUE score is still lower than LLM service, and the BLUE score shows our model understands the meaning of a sentence quite well. So this suggests that Raphael Corpus 1 Plus contribute greatly to the improvement. So in the future, we plan to evaluate our model on other tasks, such as question answering, summarization, and dialogue generation. So we also plan to enrich our dataset by collaborating with native speakers. So we try to other training methods, such as instruction tuning and TPO, to make our better flowing human instructions. So in addition, we aim to extend our model to the multimodal domain by integrating image and speech encoders. Through these activities, we plan to develop models such as Raphael VLM and Raphael SR to improve linguistic quality, expand the corpus. So here is a conclusion. So we built Raphael Corpus 1 Plus, and that is taking text large corpus from various resources. We collect web text and publications, news transcriptions, and translation data, and perform data cleaning tailored for LLM pre-training. Finally, our corpus contains more than 1 million sentences in various fields. So we carry out experiments to evaluate our corpus in machine translation tasks by applying continuous pre-training. So our corpus improves the performance compared to the original Llama 3 8 billion model. On the other hand, it is also found that our model needs to be improved to reach Google Translate and GPT-4 Mini. We should evaluate our corpus and model in other tasks, such as generative tasks. We aim to further expand the dataset and enhance Raphael for future developments. So before closing, I'd like to express my sincere gratitude to Ms. Jimenez da Costa, who provided us with fundamental knowledge of Tetun languages and supported the Raphael LLM project. I also thank Mr. Isidis Diligence Orne, who helped prepare the transcribed Tetun newsletter, use it our corpus. So I'm deeply grateful for Professor Tamura, so all members of Tamura Laboratory at Gifu University, for these continuous support, various discussions and encouragements through this research. And their collaboration and feedback made this project possible. Finally, I thank all of you here today, your attention, your interest, and your support for language diversity. And thank you very much.
Thank you. So we now have time for question from the audience. Is there any question? Okay, yes, please. The mic, please.
I was wondering, how in your paper you wrote that how can be pronounced, also written as ha with single quote u, right? There is a difference of spelling in the language. So how do you deal with that, the spelling difference in your modeling? Is it, are you using normalization, or you're letting the system to learn it?
Oh, thank you for question. And this is a maybe difficult task, but so I must deal with the future work. So, but is LLM is a large and pre-training. So I think that it may be so deal with LLM and naive architecture, deal with the spell difference. Thank you.
Okay, thank you. Is there any other question, please? Back there.
I would like to, could you share us more about how to handle the tokenizer? Because with the new low resource language, and you do the CPT, right? Continual pre-train. It means you have, if the language has some new term that the LLM should handle the tokenizer, and how do you do?
Okay, so your question is the tokenizers.
Yes.
About so, and in this research and not improve and tokenizers using default Llama 3 tokenizer. So before in this research, we conduct and tokenizer expands. So it is a model collapse occurred. So I using default Llama 3 tokenizer. Okay.
Tetun language.
Yeah, Tetun language.
The Llama 3.1 already has the vocab of the Tetun, the language you use, right?
Sorry, repeat. Sorry.
Because you use the default tokenizer, right? It means Llama 3 already has the vocab, some terms of the tokens of the Tetun and Laflag. I'm not sure the name.
Llama already has a token for
So
because it's new, already have the yeah. That's the
so and tokenizers. So maybe short words and sub words. So maybe so in Tetun language using a tokenizer, so it's maybe short subwords and generated Llama 3 tokenizers and compared English sentences. Yes.
Okay, thank you.
Thank you.
Is there any other question? We still have time. No? Okay, thank you. Mr. Nisida.
Thank you so much.
Okay, now let's continue in the realm of data development with our next presentation. Therefore, please welcome Eri Aikeda to give presentation on Japanese articulatory speech dataset acquired with 3D electromagnetic articulography. Okay, please welcome, and the time is yours. So this is next. Yes. Next is this one. Okay. This one is next. This one is previous. Okay.
Hi everyone, my name is Ikeda Eri. I'm from Kyushu University in Japan. Today I'm going to talk about our work, Japanese articulatory speech datasets acquired with 3D electromagnetic articulography, conducted in collaboration with the Tokyo University of Science. Here is the outline for today's presentation. I will be speaking in the order shown here. First, I'd like to begin with the introduction. As we know, speech comprises multiple modalities. These can be broadly categorized into three elements. First, acoustic information, which refers to the sound of speech itself. Second, linguistic information, which conveys the meaning of speech or intended message. And third, articulated information, which pertains to the movement and positions of speech organs during speech production. Access to diverse datasets for all modalities is highly valuable. As shown in this diagram, acoustic and linguistic information forms the foundation of core technologies like text-to-speech and speech recognition. Our focus, articulatory information, also plays an important role in advancing many technologies. It is used in articulation to speech, and it's vital for the development of silent speech interface. This information could also be useful for diagnostic support and speech training. Furthermore, articulatory information is used to enhance the accuracy of text-to-speech and speech recognition. To acquire the data needed for these applications, various methods exist for observing articulatory movements, but they have distinct limitations. For example, MRI captures the detailed vocal tract shape, but it requires an unnatural spin position and suffers from high noise level. Next, UTI, there is minimal physical strain on the speaker, but it can have poor visibility and doesn't capture the lip. For this study, we chose EMMA, while EMMA has its own limitation. It can track only the point of coils. It avoids the critical issue of noise and unnatural posture. And most importantly, it provides the excellent temporal resolution we need to capture the rapid and detailed movements of speech. However, there is next problem, a significant data gap. While several publicly available datasets using EMMA exist, they are overwhelmingly designed for English-speaking populations. English is a stress-timed language. However, Japanese is a typical mora-timed language, where each mora has an approximatory co-regulation. This creates unique rhythmic properties. And for Japanese, while some data standard speech corpora, that is, audio and text, are arrivable, but there is almost no publicly available data, especially from EMMA. Therefore, constructing a Japanese dataset is significantly important. The dataset from this study can contribute to language with fewer speakers or limited data resources. So this brings us to the purpose of our study. Our main goal is to address the lack of Japanese data and help make speech technology more accessible. To achieve this, our study constructed a dataset of 3 synchronized datasets plus corresponding level data. The 3 synchronized streams are speech audio, articulatory movement, and vocal fold vibration, and additionally automatic phoneme segmentation levels. Next, I will explain our method. Now, I will detail the overview of this dataset. Speech and articulatory data were collected from 4 native Japanese speakers, 2 men and 2 women. 3 of these speakers had received speech training. Each speaker produced approximately 37 minutes of speech for a total of approximately 150 minutes of data. The spoken material was ATR 503 corpus. This corpus consists of 503 phoneme balanced sentences, which are further divided into 10 subsets of 50 sentences each. For ethical considerations, our study was approved by Kyushu University Ethics Research Committee, and all subjects provided informed consent. This slide shows our measurement setup. All recordings were conducted in a soundproof room. The hardware we used for each data is listed on the left, and the overall system configuration is shown in the diagram. The most important point of this setup, highlighted in the yellow box, EMA, ECG, and audio, all signals are routed through a single AD converter, ensuring they are perfectly synchronized into the PC. After recording, the data was processed. For audio and ECG, the data was sampled at 50 kHz and then processed using a high-pass filter to reduce noise. For EMA data, we used a sampling rate of 250 Hz. As shown in the diagram, the 6 green circles are our articulatory observation points: upper lip, lower lip, low jaw, and the tongue surface 3 points. And the 3 blue triangles are reference points for head correction. The plate shape was also acquired. Finally, noise was removed using a low-pass filter. We also confirmed the technical accuracy of our system. The estimation accuracy is within 0.5 millimeter under ideal conditions. That ideal condition is right? That is when the receiver coil has no angular deviation. And this graph shows what happens when the coil are tilted. Like the blue bars, when the tilt angle exceeds 20 degrees, the error can approach 1 millimeter. However, we have confirmed that tilt is within 10 degrees from the yellow bar. The impact on accuracy remains limited, staying near the 0.5 millimeter line. While we can't measure the coil angle in the real time. So we tried to replicate this ideal condition as closely as possible. Beyond technical accuracy, we also ensured the procedural consistency. That ideal is that coil will remain in the exact same position for all sentences, but however, it is challenging. The receiver coils are susceptible to saliva and time, causing them to dislodge. It is very difficult. So our solution was use the structure of the ATR 503 corpus. As mentioned, the corpus consists of 10 phoneme balanced subsets. We used these subsets as our recording unit. If a coil was dislodged, the recording was restarted at the beginning of that subset. This procedure is our result. It ensures consistent coil placement within 850 sentence phoneme balance subset. For the level data, we use automatic annotation process. As shown in this diagram, we prepared 2 inputs. First, downsampled audio at 16 kHz. Second, the corresponding hiragana transcript. These 2 inputs were fed into the tool, which is the Julia segmentation kit. The output from this process is time-aligned phoneme levels within 10 millisecond resolution. As you can see in the example output box, this provides the first time, the start time and end time, and the specific phoneme level. Now for our summary. Using this dataset, we can analyze the data. For example, we can see that exact articulatory position when a specific phoneme is pronounced, and at the same time, We can check the EGG waveform to know if it was a voiced or voiceless sound. I play now the video of data. For the articulator position in the video, please refer to the color and shape in the central diagram. First, I play the data from a male speaker.
生きた潤滑油です。
Sorry, it is no audio. Next is female speaker.
生きた潤滑油です。
Sorry, next. To summarize, we constructed a reliable dataset for four synchronized data type, audio, EGG, EMA, and labels, from 4 native Japanese speakers, as you can see from this specification on this slide. Finally, I will discuss our future plans and acknowledgement. For our future work, first is expected utility. This dataset is expected to be useful for research on articulatory speech conversion and for broader studies on low resources language. For data arrivability and expansion, the dataset will be made publicly available and expanded in the future. And finally, for data refinement, the current automatic label will undergo refinement through manual annotation using IPA. I concluded my presentation. Thank you for listening.
Thank you. Okay, now are there any questions for the presenter regarding her work? Okay, any? Okay, no, so I will ask you a question. So what is the core motivation for creating this data set? So what is the relation between the articulatory data set with the more timing type of language? Because in the introduction you mentioned about your the Japanese is a more timed language, and then what is the relation between your data set that you just built with the kind of language?
I think that Japanese is a more time language, and it has unique rhythm. And I think this data contributes to the during the unique rhythm の間に how move the articulate point, or we can understand what's the tongue and lip move.
Okay. Okay. Are there any other question from the audience? No? Okay, thank you.
Thank you.
Miss Ikeda.
ありがとうございました。Thank you.
Now shifting our focus to the area of speech science, I'm pleased to introduce our next presenter, Yuan Jia. Please welcome Yuan Jia. Already coming or not? The committee, Yuan Jia. Actually, Yuan Jia will be presenting the work on production pattern and prosodic features of Chinese tones by learners from 5 Central Asian countries. So it's not present yet? Okay, thank you. Because Yuan Jia is not here today, so I will move to the next presenter. Now welcome Ziwei Wang, who will be sharing valuable research with title Is Beijing Mandarin Stressed Time? Examining Rhythmic Patterns in Spontaneous and Rich Speech. Please welcome Ziwei Wang. But actually, Ziwei Wang will be delivering their teamwork presentation online. Please prepare the Zoom. Thank you.
Okay. Okay, thank you very much. Can you hear me and see my slide?
Please hold on. Okay, now you can
Okay, can
start.
you hear me? Hello?
Yes, we can hear
Okay,
you.
okay. Good morning, everyone. I'm Zhu Wang, a PhD student from University of Chinese Academy of Social Sciences, and my talk is titled "Is Beijing Mandarin Just Timed? Examining Rhythmic Patterns in Spontaneous and Read Speech." Thank you for the opportunity to present. Let me begin with the background and significance that motivated this study. So rhythm, defined as a regular perceptual patterning of prominent elements in speech or poetry, constitutes a central aspect of prosody in spoken interaction. Speech rhythm demonstrates considerable variability across languages and dialects. Speaking styles and genres, individual speaker characteristics, communicative intentions, and emotional states. So based on the hypothesis of rhythmic isochrony, languages are typically grouped into stress-timed, syllable-timed, and moral-timed categories. And in stress-timed languages such as English, the interval between stressed syllables are preserved as roughly equal, leading to compressed, unstressed syllables and frequent vowel reduction. In contrast, syllable-timed languages like Spanish and French maintain more consistent syllable durations with similar syllable structures and minimal vowel reduction. Moral timed languages such as Japanese are instead based on equal moral durations. And traditionally, Chinese has been described as a tonal and syllable timed language, both pitch and duration shaped rhythm organization. Yet, the rhythmic classification of Beijing Mandarin remains controversial. Some studies claimed to be stress-timed, while others consider it syllable-timed. Importantly, most of these studies focus on phonological or word-level analysis and rely on limited read-speech data. And native speaker institution, as well as emerging experimental evidence suggests that speaking style plays a crucial role. Spontaneous speech in Beijing Mandarin tends to exhibit more stress-timed features than read speech. So recent research has emphasized this variability, proposing that speech rhythm should be viewed as a continuum and multidimensional phenomenon. And following this new perception of shaping rhythm patterns, we examine two questions. First is the rhythm matrix between read and spontaneous speech of Beijing Mandarin, and the difference in rhythm matrix between Beijing Mandarin and American English. So I will now outline our database and the rhythm matrix. The database includes three-part read speech material, spontaneous speech materials, and American English. And there are some introduced of our database. And then we computed established duration-based rhythm matrix, noting that C and V to the initial and finals in Chinese syllables. Interval measures included pairwise variability indices. Duration and the ratio measures included mean durations and the proportion of vowel duration. Variability measures included the standard variations and the vocal. We also calculated monalized and raw PVI. Finally, we measured fluency using speech data, speech rate and articulation rate. Okay, and then I will introduce some key findings and discussion. In this section, we compared the rhythm matrix of two Beijing Mandarin speech styles. Characteristical analysis revealed significant differences in rhythm matrix between these two styles. Notability, variability matrix for segment duration were found to be higher in spontaneous speech, and indicating that vowel and consonant durations are more variable in spontaneous speech. And both mean C and mean V exhibit a broader distributional range in spontaneous speech, whereas reading style engender a more homogeneous duration pattern. And both SR and AR are significantly higher and more variable in spontaneous than in read speech. And this finding indicates that Beijing Mandarin, when spoken in spontaneous speech, manifests markedly greater rhythm variability and flexibility compared to reading. And then to access ways which rhythm patterns read speech or spontaneous speech more closely align with the stress-timed rhythm, we compared the rhythm matrix of two speaking styles to the English rhythm matrix. And there is some results. The analysis reveals distinct rhythm differences across languages and speaking styles. American English exhibits the highest NPVI-V, but the lowest RPY-C values, reflecting strong vowel variability and stable consonant timing. In contrast, both speaking styles of Beijing Mandarin shows higher NPVI-C values than American English, with spontaneous speech yielding the highest overall. And similarly, Data C and vacuum C values increase in spontaneous speech, indicating that enhanced consonantal variability approach to a pattern of stress-timed languages. And then cosine distance results further support this tendency. Spontaneous Beijing Mandarin is acoustically closer to American English than its own reading style. And overall, this finding shows that while reading Beijing Mandarin remains largely syllable-timed, its spontaneous speech shifts towards stress-timed characteristics, reflecting dynamic rhythm adaptation across speaking styles. Together with this previous research, our results suggest that rhythm exists on an continuum from syllable-timed to stress-timed, and both across and within languages, and even between speaking styles of same dialect. Statistical analysis further confirmed that Beijing Mandarin demonstrates distinct rhythm characteristics across styles. In the reading style, the data and PVI-V values resemble those of syllable-timed languages like French and Spanish. And in spontaneous speech, however, these values move towards just-timed pattern typical of English and German, showing greater duration variability. The spontaneous speech still thus display intermediate rhythm properties, supporting that argument most languages occupy a continuum rather than instinct categories. And these findings also agree with that the rhythm varies within classes rather than conforming to fixed types. And several linguistics and phonetic factors help explain this variability. As first observed, rhythm matrix reflect phonetic realization rather than phonetic categories. In spontaneous Beijing Mandarin, greater prosodic variation and greater frequency of neural tone syllables strongly influence rhythm measures. Comparing dialects cantonese lacking unstressed syllables shows ever a strong syllable-timed traits, though both dialects are shaped by speaking style. And the rhythm difference between reading and spontaneous speech also reflect conscious adjustment to communicative needs. In conversation, speakers may lengthen key syllables or enhance contracts of emphasis, resulting in higher data and NPVI values. And emotional expression adds further variation. Joy or surprise often involve a prolonged syllables, and while reading style is emotionally neutral and more rhythm stable. And beyond emotion, spontaneous speech involves ongoing adaptation to context and listener feedback. Speakers slow down for new or important information and accelerate for familiar material. And in cognitive, spontaneous speech prioritizes communicative efficiency, allowing greater rhythm fluctuation, and as indicated by high C values. And meanwhile, reading tasks prioritize presence, resulting in more stable rhythm patterns. And from a social point of view, rhythm variation also expresses relational meaning, rhythm entrainment. The adaptive behavior contributes greatly in Beijing Mandarin's higher rhythm variability in spontaneous interaction. Okay. And it is also essential to recognize the method factors such as corpus composition, speech rate, and style, which can influence rhythm metrics and sometimes obscure cross-language characterize. For example, in our data set, the RPYC of American English are unexpectedly lower than that of Beijing Mandarin, likely due to the sentence structure differences and the sample imbalance. And phonologically, Beijing Mandarin has been described as a syllable timed. Yet this results review a rhythm continuum depends on speaking style. And reading speech shows more balanced and regular timing, whereas spontaneous speech exhibits greater variability shaped by emotion, emphasis, and social context, promoting stress-timed rhythm. And in conclusion, Beijing Mandarin demonstrates rhythm diversity modeled by linguistic, connective, and social factors. A rhythm in this language, and likely in human language more general, is not fixed structure trait, but a flexible and adaptive feature of spoken interaction. Though our English data are limited, future work will expand cross-dialect analysis and explore rhythm through pitch-based approaches to deepen the understanding of Chinese prosody. Okay, that's all. Thank you very much. And if you have more questions and want to discuss, please contact via email. Thank you very much.
It's interesting result, yeah, for the presentation. So it's different style between read speech and spontaneous speech in Beijing Mandarin. Okay, is there any question for the presenter? Okay, please.
Yeah, hi. I don't know if the presenter can hear us now. Can you hear us?
Hello,
Okay, I can hear.
Yes.
Okay, super. So I had one question. A lot of times these rhythm measures, that rhythm matrix measures that you have taken, they depend on the syllable type. I also understand that Chinese has limited syllable types, which could be probably CV versus CVN, which the nasal being in the coda. Okay, so the read speech and the spontaneous speech may be variable in terms of the syllable type, number one. Number two, the read speech and the spontaneous speech may also be different in terms of their tonal variation. And we already know that in Mandarin Chinese, tone 3 is much longer than, let's say, tone 4, etc. So possibly when we are doing these kind of, rhythm matrix analysis, other factors which might contribute towards to the duration of the syllables may also be taken into consideration. And this is a shared problem. I faced that problem. That's why I'm sharing with you. Maybe you have some solutions. I would like to know what your solution or if you have any response to that. Thanks.
Okay, thank you very much. That's a good question. And this question is always in our consideration. And you mean the different tones and different syllable structures will influence the result of rhythm computed. Maybe in this research we just use the rhythm matrix based to the duration. And if you can see some research in Hearst, you can find some pitch-based rhythm matrix to use to compute the rhythm. So I think in the future study, we will use a pitch-based rhythm matrix to compute the rhythm types in our future study. Okay.
Thank you.
Thank you very much.
Okay. Is there any other question? No? Okay. Is there the presenter for paper 18? They're already here, or we just skip? For the presenter number 18, paper number 18, so the presenter are not here, so we just skip it. So because of the authors of paper ID 18 are not here, so that we just close. So that brings us to the end of our final presentation for this session. I would like to thank all 6 presenters for their insightful research. And I also thank you for your contribution and active participation. I will now hand the floor to the member of Master of Ceremony. Thank you very much.
Yeah, thank you very much, Dr. Kurniawati Aziza, for guiding the session. And also our sincere appreciation also goes to all presenters, both on-site and also online, for your engaging and inspiring presentation during the oral session 4. So let's give a big round of applause to our session chair and all of the presenters once again, and also for the collaborative spirit of O-COCOSDA 2025. So, ladies and gentlemen, we will now take a break for lunch, which is available right outside of this auditorium. Please take this time to relax, enjoy your meals, and continue connecting with fellow participants. We also have information for participants who have requested vegetarian meals. Your lunch will be provided at the registration table. You can collect your meals at the registration table at the back. But you are also welcome to get your meal from the main food stall outside. Kindly check the description so that you may choose what suits your preference. And after lunch, we will continue with oral session 5, starting at 1 p.m. So we kindly remind everyone to return to your table a few minutes before 1 p.m. so we can start the session on time. And I would also like to remind the members of the steering committee that there will be a lunch and meeting in room K05, located lower floor of this building. We invite the steering committee to gather near the stage areas shortly, so that our student assistant can accompany you to the meeting room. Once again, thank you to all our speaker, participant, and our session chair for a wonderful morning session. We wish everyone a pleasant break, and please enjoy your lunch. Thank you.
Recording stopped.
Jakarta, yuk, berangkat sekarang yuk, Jakarta yuk.
Hati-hati ya.
Ibu baik-baik di rumah ya Bu. Pamit ya.
Selamat pagi Bu. Selamat pagi Mbak. Pagi Pak.
Ini adalah kisah kami tentang harapan dan mimpi akan sebuah tempat yang penuh kemajuan dan inovasi. Kami tak hanya menuliskan barisan kode dan coretan tanpa arti, tapi solusi nyata untuk berjuta kehidupan setiap hari. Dan ini bukan hanya soal membangun aplikasi, tapi membangun sebuah warisan. Dan kami bukan sekedar talenta. Kami adalah penulis masa depan. Kami percaya masa depan teknologi harus dikuasai negeri sendiri dan dibangun oleh anak bangsa yang berani bermimpi.
Fokus untuk tenaga-tenaga ini handal di bidang science, teknologi, engineering, dan mathematics.
Dan ini bukan sekedar tempat kami bekerja, tapi juga wadah untuk belajar dan membuka cakrawala dunia. Tempat kami menggantungkan harapan, memberi layanan, dan membangun jembatan masa depan. Karena inovasi tak hanya untuk hari ini, dan masa depan bukan soal garis tangan. Dan kami percaya kemajuan teknologi tak selalu tentang kecepatan, tapi juga soal keberpihakan. Kepada segenap rakyat Indonesia, kami percaya pasti ada jalan, bukanlah sekedar slogan. Dirgahayu Indonesiaku, dari kami, karya anak bangsa yang berjuang untuk Indonesia.
As the world we live in keeps on evolving, we become more reliant on technology. From businesses to our everyday lives, everything needs to be easier and more efficient, so that we're able to utilize our precious time better. We created technology beyond space and time and made everything possible. So, who made it? Glare.
Us?
Yep. They are the creators from Glare, the top minds of the country, professional, creative, and always innovative. Glare, your technology partner, to help you accelerate and be efficient. We integrate the things that you always wanted to have in your business, such as AI, cloud, mobile, most importantly, in a secure and affordable way. Hey, Michelle.
Oh, hi!
Can you tell me what solutions Glare provides?
For sure! We provide quite an array of solutions. Let me show you. Here's a great way to arrange your product display. Hi, Sheila. Oh, hi. With Planogram, you only need to take a picture of the display and instantly your layout is checked, so you can determine the best layout for your display that can increase sales in a cool way. Absolutely. Want to know how you can maximize your inventory? We have demand forecasting, a technology that can predict the demand of your products in the market. Being an integrated system, there will be no more inventory challenges in your supply chain.
It's all connected.
The future is here! With OCR technology, all you have to do is scan your documents, then all physical data will automatically be digitized at your fingertips.
Well, that's fast.
Glare will protect your banking system with fraud detection technology. Suspicious transaction will be automatically detected so that your banking staff can rectify it immediately.
Don't worry, we'll figure it out.
That's awesome.
I know, right? AI is definitely beyond what we've imagined. From face recognition that we use daily for online payments, to vehicle detection in law enforcement, and deep dive analytics for your customer that can help them make accurate decisions.
There's so much more that Glare can do. Let's collaborate and join us in your transformation to the future.